Okay, this is a quick video about torque, tipping, and something called fictitious forces, which we'll talk about at the end. The question we want to answer with this video is, what causes a bike to not tip? Or what causes a bike to tip? First, we want to look at a bike at rest, okay? And so let's just say that this person has a center of mass, including the bicycle, that's located some distance above and in front of the rear wheel. It'll be clear in a minute why we want to label things in terms of that. Okay, what prevents this bike from falling through the ground and toppling over? Normal forces. And notice I have two here. I'm not making the claim that they have the same size. In fact, they don't have the same size. That's kind of the whole point of this video. We'll transition to a schematic just to make things a little bit easier to see. Okay, and what's the point of accumulating all these forces? Well, we're gonna make a free body diagram, right? We make a free body diagram. You've got the normal forces pointing up, you've got gravity pointing down, and we write our equation of motion. It's pretty straightforward at this point. The other thing that we need to do, though, notice we have two unknowns, so we need another equation, and that comes from torque. So the first time we'll do this really carefully. The rest of the torques I'll let you handle, but let's work through one together. So torque is always R cross F, so that ends up being the lever arm times the normal force times the angle between them. So in this case, on the rear wheel, if we're taking the torque about the center of mass, this is the lever arm, RR. It's this distance. The force points up, and so what we want is the sine of this angle. The sine of this angle, okay? The sine of this angle is whatever is opposite it divided by the hypotenuse. What's opposite this is D. Likewise, I can make the exact same argument over here. This angle is theta. This is L minus D. In other words, the two wheels are L apart. And if I make that substitution, it looks something like this. Okay, now I have two equations and two unknowns. If I solve them, I end up with something that looks like this. Notice that the normal force is not mg over 2. That's because the center of mass is closer to the rear wheel. And you can imagine if this person leaned back even more, that the normal force, so that would be decreasing D. If D goes down, the normal force goes down. That means that if you shift your weight back far enough, eventually there will be no normal force on the rear wheel at all. That's something that we're going to start to be very interested in when we talk about tipping. Okay, so much for that. You'll end up with that nice result there. Let's make it a little more interesting by putting him on an angle. So it's the same guy as before. I haven't changed anything. I've just now said that there's some angle here. Now let's see what we need to do in order to prevent him from tipping. Well, we got a free body diagram, just like we did last time, only now, look, I had to add something. I had to add something in the horizontal direction, and I added more arrows down here. Why is that? Because if you're on a hill, there's a force of gravity points down the hill. Now you need something pointing up the hill in order to prevent you from moving, and that something, of course, is friction. Now, I just put it as a big F here. Technically, there's a friction force from the front wheel, so that would be like FF, and a friction force from the rear wheel, which you could call FR. I don't really care what those forces are, but I'm there, and maybe we'll look at them later. Okay, so we have this free body. We use it to make our equation of motion. That's in the perpendicular direction. We do it again in the parallel direction. And you might say at this point, wait a minute, why do you keep saying F? Isn't F mu times the normal? Okay, plug that in, grind through the algebra, and see if you get anything useful. The short answer is you won't. So we actually do need to keep going. Also later, when we allow the bike to roll, the force of friction does not equal mu times the normal anymore, and we won't be able to do it anyway. So just for generalness, let's keep going. If I take the torque about the center of mass, notice, look, I've got 1, 2, 3, 4 unknowns and only 3 equations. So this is bad. So instead what we're going to do is something a little weird. We're going to take the torque about the rear wheel. So if I take the torque about the rear wheel, the advantage is that these forces, since they are located at the rear wheel, they don't create any torque. And you won't see them referenced in this torque equation because they're 0, right? That's really good news for us because it means, let's just set this up. Our new lever arm is here to get to this force. The normal force points up and it creates a tipping action, you could say, in the clockwise direction, so we put a minus sign. The friction doesn't contribute either because it's parallel to the distance from the pivot to the force. So this is a remarkably easy torque equation compared to the one above it. And now we're actually in a position where we can grind through some algebra. And if we do, okay, fine. It looks a little uglier than it did before, but I've written it in a very suggestive way. Look at this. Look at this. They're very similar. In other words, it's just a modified version of what we saw earlier that depends on theta. One very interesting case to consider, let theta equal 0. If theta is 0, cosine of theta is 1, and tan theta would be 0, which means we just recover what we recover on flat ground. So this is a good sanity check for us. This makes sense. Another thing to consider is that as theta gets larger, this thing will get larger. If this thing gets larger, you're subtracting it. It means that the normal force on the front wheel will get smaller. In other words, if I make theta a special angle, eventually I'll have no normal force on the front wheel. Let's take a look at what that looks like. Maybe you know that an object is stable if its center of mass is above its base. Well, let me drop a perpendicular. That's where his center of mass is. Indeed, it's above the base the way I've drawn it right now. What happens if I tip him? Now he's just at the tipping point, And when I do this, tan theta is d over h, meaning that if I tip the bike enough so that tan theta is d over h, he will tip. Now what happens if tan theta equals d over h? Oh my gosh, if you plug that in, the normal force will be 0. In other words, if you're on an incline and you lean back on your bike and you make the distance too small, you are going to tip over. Okay, so what does that mean? It means you go flying and you hurt your head. So let's not do that. This is if tan theta is greater than d, this person's going for a ride. Okay, so let's put him back on safe ground. There he is. We're back to the bike at rest. Now what I want to examine is this. Not that he's on an incline, but that he's going to accelerate. You might say, oh, okay, well, probably the same thing as before. And actually, it's very similar to before. Let's set it up. Let's make our free body diagram. Why do I have friction in this case? Because he has to accelerate in the forward direction. I need some force there in order to push him forward. Okay, so let's make our equations of motion. The forces are pretty straightforward. This looks a lot like it did before. This one's different. Instead of being equal to 0, now I've got an ma there now. Okay, let's do the torque as well. If I look at the torques again about the rear wheel, I end up with this guy and this guy. So what's different? The thing is that because the bike is accelerating, I can't set this equal to 0 anymore. It's equal to I alpha. And you might say, wait a minute, there's no alpha, the bike's not rotating. It kind of is since we're taking the torque about this point. Let me show you what I mean. This acceleration vector has a component that is in the tangential direction according to this guy. It's got a centripetal in the other direction. So if it has a tangential acceleration, it has an alpha. It's really weird, guys. If I took the torque about the center of mass, I would find there is no alpha. But there is an alpha about that point. So we're going to have to deal with it. That's kind of the price we pay for eliminating variables. So let's work our way through this. The tangential acceleration is the component of A that lies along this direction. Okay, well, if this angle is theta, and this angle is theta, and this angle is 90 minus theta, then this angle is 90 minus 90 minus theta. So this angle actually is theta. And so A tangent is A cosine theta, and then the cosine of theta, look, that goes like this side. So you end up with an H. What about the moment of inertia? Well, look, the center of mass is just a point particle a distance r away, so it contributes to a moment of inertia, mr squared. Easy peasy. So if we plug these in, we end up with something that looks like this. So you end up with an MAH on the other side, and if we go ahead and we solve this, okay, not so bad. We actually get the same normal force that we had at rest on flat ground minus some acceleration term. In other words, this is the interesting thing. The more he accelerates, the less force there is on the front wheel. Is there a way he could accelerate enough to lift his front wheel up off the ground? Of course, that's what popping a wheelie is. Let's park this result over here. I now want to give you a slightly different way of getting the same result that's going to, I don't know, it might bother some of you if you've never seen it before, but it's actually very interesting. What we're going to do is we're going to do the same problem in the frame of the bike, which is non-inertial because, remember, the bike is accelerating. So what does that mean? That means that he says, I'm not accelerating, you are. But he feels something funny because when you're in a non-inertial reference frame, you end up feeling like there are forces. Imagine playing pool in the back of a truck and the truck starts to accelerate and you say, I'm not accelerating, it's just that the pool balls keep moving in weird ways. Yes, you'll end up with weird forces. So this person has decided that they're not accelerating. There just happens to be some force that they can't see that is pushing them backwards. That's what they feel. It's very weird physically to talk about this, but mathematically it actually makes things a little bit easier, which is why people do it. These are called fictitious forces. So now in the x direction, we have friction pushing forward and this fictitious force, this F, pushing in the opposite direction. For the torque, I do the same thing, and now instead of having to decompose this acceleration vector like I did before, which was kind of annoying, I just have another torque due to some force that points in this direction, and it's pretty easy to work that out. Now, some of you might be looking at this and being like, wait a minute, those are the same equations you had before. You just took the thing that was here and moved it here, and the thing that was here and moved it here. yeah, that's why this works algebraically. Whether or not you take it seriously is another thing. But this trick works. You end up with, of course, the same value that you had last time. If you're wondering how seriously to take all this physical stuff, here's another thing to consider. According to this guy, there's some net force pushing him down and to the right. And that net force depends on his mass in both cases. The mass depends on g for his weight, and then this other thing also depends on his mass. That means that as far as he's concerned, the force of gravity has shifted direction and now points downward. What does that mean? Well, let's fix gravity so it points downward again. Holy Toledo. He is back on the inclined plane. As far as he's concerned, the same thing is happening that happened last time. What does that mean? That means that you'll tip at A over G equals D over H. Plug this in to this equation. That's what we got on flat ground. You'll get 0 for the normal force. But compare that to what we got for the inclined plane. Tangent of theta was D over H. Holy smokes. It turns out that it does not matter whether this guy is on an inclined plane and the apparent force of gravity points down and to the right, or if he's on flat ground and accelerating forward. This may seem like just a cute little calculational trick, but it's actually related to something called the principle of equivalence. You cannot tell the difference between a gravitational field and acceleration. This is one of the big things that led Einstein to consider his general theory of relativity. There's a lot you can do with this, but for this guy, for now, he just says these fictitious forces are awesome because it helps him do awesome wheelies. Hopefully this video was more helpful than confusing.